This is for what are called, this is not always true. This is was for what are called ohmic materials. Ohmic materials follow Ohm's law that we'll talk about in a minute. So resistance, wish I had a chunk of metal here. I could point to something. Here I got like this back scratcher. This is a galvanized steel, I guess, probably. Stainless steel, maybe. All stainless steel in my house, it's all at the same temperature, has the same resistivity. It all has the same rho. That's something you would look up in a table. This particular item I have here, this cylinder, has a certain amount of resistance. And that depends on the length divided by the cross-sectional area. So I've got, say, some cylinder. So here's my length. Say here's my radius. Then my cross-sectional area would be pi r squared. My length would be L. So the total resistance of this cylinder here would be stainless steel's resistivity at room temperature times L over pi r squared. This, I got one of these little head scratchers here, right? Let's assume these are the, I don't know if they are, but let's assume they're the same material. And I look at one of these little tines here. These two things have the same resistivity. This guy's going to have a lot less resistance. Oh, let's actually work that out and see. They're the same length, roughly. Let's pretend those are the same length. But my cross-sectional area here is much smaller. So if I divide by a smaller number, I get a bigger number. This guy has more resistance than this guy does. A good way to think of resistance is like traffic flow. Like imagine you're on a highway and resistance is like what's impeding you from moving down the highway. Who's in your way? Well, if you make the road bigger, if you increase the size of your road, now you've got more lanes. Now there's less resistance to you moving. If you double the length of your road, though, now you got more stuff you got to get through. That's going to increase your resistance. Hey, so a good problem to do is say, okay, we've got some, oh, by the way, this is in ohms. So resistivity, rho, is in ohms times meters. Let me check my units there. Ohms per meter. The unit for ohm, 1 ohm is volt per, I have to think about it, 1 volt per amp. Resistivity then is in ohms per meter. And we just look at units here. I think it's ohm meters. Yeah, ohm meters. I always want to put that in the wrong place. Ohms times meters. Ohms times meters times another meters divided by meters squared, we just get as ohms. So I've got some chunk of material here, has length L, cross-sectional radius R, say it's a cylinder, and let's say this guy has resistance, some R naught, some initial value. What happens if we double L? What will the new resistance be? Well, our resistance will be rho times 2L over pi r squared, which if I pull that 2 out, is twice my old resistance. That was R naught. R naught was just rho L over pi r squared. And that part's pretty easy, right? If I double the length, I'm going to double the resistance. What if I double R? If I make the thing twice as big in terms of thickness, well then R, let's maybe call that R1, R2 will be rho times L over pi 2R squared. I got to square that 2 now. I get a 1/4 rho L over pi r squared. That's what I called R naught. So because we have that R squared in the bottom, doubling the radius does not cut the resistance in half. It cuts it down to 1/4. What if we do both? So what if I just literally double all my dimensions? This is counterintuitive. You wouldn't expect this. You would think everything would be proportional. If I just take this thing and blow it up so that it looks exactly like a blown up version of that. If I double all of my dimensions, L and R, the radius, it just now occurred to me that this whole problem, I'm using R to mean two different things. Let's call this guy little r for our radius. I'm sorry if that confused anybody. I was writing R to mean the radius of the cylinder here and the resistance. And you should never use the same letter to mean two different things. I apologize for that. So let's double L and R. Then my new resistance will be rho 2L over pi 2R squared. I get a 2 on the top, a 4 on the bottom. I get 1/2 my original resistance. So doubling both cuts your resistance in half. And that was assuming we had a cylinder. If we had a rectangle, then our area in the bottom would be length times width. And we would get a similar result. Okay, we have a resistivity written assignment coming up where all that's going to apply. Okay, ohmic resistors, by definition, what makes something an ohmic resistor? It follows Ohm's law. It's kind of a redundant name. Ohm's law says in an ohmic resistor, V equals IR. The potential drop, so this here, V, we always write V equals IR, but that's VAB. The potential drop across a resistor is the current times the resistance. So if I had a battery here going through a resistor, so this is our circuit diagram element for a battery. So notice I have the two lines, but one's bigger than the other. Capacitors, these would be the same. This is our circuit element for a resistor, a little, that should be like nice straight lines. So say this is a 10-volt battery. This is our positive side. This is our negative side. The big side's the positive side. That's the side current flows out of. Again, we assume conventional current, that positive charges are moving. Here's some resistor, R. Let's say he's a 2 ohm resistor. Then this battery has a whole bunch of positive charges here and negative charges here, and it keeps building new positive charges here. Those want to get away from each other, so they run. So my potential rise to get from here to here is a potential rise as I go through this resistor, I'll get a potential drop. And how much do I drop here? V equals IR. And that will be 10 volts. I'll have a 10-volt drop across this resistor. And so 10 equals I times 2. I will be 5 amps. And I like to think of current literally like water flowing through a water pump. So think about those water pumps you see, those little fountains. So you got a hose, here's water flowing, and then the water, I don't know, maybe flows up and then trickles back down into some pool down here. And then the pump lifts the water back up. The water, I don't know, maybe the water sprays up here, who cares? The water falls back down into this pool and gets pumped back up. The pump is the battery. That takes work, that requires energy to get those charges from ground level up to the top. This is a very good analogy. The pump is a battery. It lifts your charges up to a higher potential. Here's say V equals 0, here's V equals 10. The battery lifts you up to a high potential. As you pass through the resistor, you get a potential drop. And we dropped 10 volts. Then we go back to the battery and get lifted up again. So that's energy. The battery uses energy to get those charges up that hill, and then we drop. If we had a bunch of resistors, we would lift up and drop and drop and drop. That requires energy. Where does that energy go? It gets dissipated by this resistor in the form of heat or light. That's what a light bulb is. A light bulb is nothing but a resistor. Like an old incandescent light bulb is a resistor that gets so hot that it glows. Well, how much is it? How much energy is it using up? We call that power. P, and that's I times V. This, of course, is in watts. It's power. But we know V equals IR. So I could, if I have an ohmic resistor, plug that in there and say P equals I squared R. Or I could solve this guy for I and plug this in here and say P equals V squared over R. Any of these forms, we got 3 different formulas for power, and whichever one's the most convenient is the one we use, which if we know 2 of those things, we use those to find power. They all give us the same number. This is how much energy your resistor is expelling in the form of heat or light or mechanical energy. So you look at a light bulb and it says it's a 10-watt bulb. That means, so say I have a light bulb here. If that's 10 watts, and I plug that, say, into put it on a 9-volt battery. So this is how much voltage is available to me. This resistor, and that's all it is, will draw a certain amount of current, so that P equals IV. I then will be 10 divided by 9, which is about what, like 1.11 amps. So that current will draw a little over 1 amp to get 10 watts. It's our wattage that it determines our brightness. So we're going to have problems later where we say we hook these up in series. What kind of brightness do we get from each one? If we hook them up in parallel, what kind of brightness do we get? And all of those, we're going to calculate our power that actually goes through the bulb. Okay, that's really the entire chapter. I really should squish this chapter in with capacitors because there's really not much there. We start using this term here, electromotive force. In all of science, this is the worst named object in all of science. We're going to be talking about EMF the rest of the semester. It is not a force. It has force in the name, but it is not a force. It's a voltage. EMF is just voltage. That's all it is. It's a stupid name. I think Michael Faraday came up with it because he didn't, like, all of our physics SI terms had not been developed yet. And it's a holdover, it's a carryover. We've been saying EMF for 200 years now, and we really need to stop saying it. EMF just means voltage across a battery. Okay, there's some pictures for circuit diagrams.